This is welding. Welding by explosion, an unexpected technique to connect two structural elements. The explosion creates a shock wave which bonds the atomic structures of the parts. Bonding of atomic structures. This is the basic idea behind welding. Based on the nature of the energy source, various welding processes have been developed. Here, welding with the aid of human energy, by forging. This method was already used in Roman times, for example, for pile shoes. Or using mechanical energy, welding by friction. Some connections are made by ultrasonic welding. Thermochemical energy is used in oxy-fuel gas welding and in thermite welding. Laser welding uses infrared radiation at ambient atmosphere. A similar process is electron beam welding, using a stream of electrons in a vacuum. Electricity can be directly used as an energy source, for instance in resistance welding. For welding rails, electricity is also the energy source. Flash butt welding. Electroslag welding is another form of welding with electricity as the source of energy. The electric current flows through the flux, which is added to cover the weld pool and thus generates heat. All these processes are important in specific situations, but in general not very useful for the steel construction industry. For this discipline, the most important welding process is arc welding. Welding. What actually happens in this rather complex process? Welding depends on local melting of parent metal, usually in combination with a deposit of molten metal produced by a consumable electrode. The liquid weld metal forms the weld pool, which, after solidification, forms a continuous connection between the structural elements. The metallurgical phenomena in the weld pool and the adjacent heat-affected zone are mainly determined by the local maximum temperature and the subsequent cooling. A time-temperature diagram describes a typical welding cycle. The peak temperature decreases rapidly with increasing distance from the weld. The cooling rate depends on the thickness of the plate and on the heat input. The thicker the plate, the faster the cooling rate. Preheating reduces the cooling rate, which is particularly important to avoid the formation of martensite. In a single pass weld, different zones can be distinguished. The zone of the weld metal, in most cases a mixture of deposited material and molten parent metal. The zone adjacent to the weld metal, the heat-affected zone consisting of heated parent metal, and the unaffected parent metal. Let's look at the different zones more closely. When the weld metal solidifies, long and narrow dendritic grains are formed. These dendrites grow in the direction of the maximum temperature gradient starting from the fusion line. It's at this line where the heat-affected zone begins. In case of structural steel, this heat-affected zone comprises three different sub-regions. The first region, close to the fusion line, rises to temperatures higher than 1100 degrees Celsius. Here, the ferritic steel is transformed into austenite, and due to the high temperature, austenite grain growth takes place. On cooling, this region then transforms into a ferritic structure termed a coarse Wittmann-Steffen structure. The second region is that heated to between 1100 and 910 degrees Celsius. The ferritic steel is also transformed into austenite, but here the grain size is reduced during cooling, termed fine Wittmann-Steffen structure. In the third region, heated to between 910 and 730 degrees Celsius, partial transformation into austenite takes place. Depending on time and temperature, this austenite contains a relatively large amount of carbon, an area with degenerated pearlite. If the carbon content is higher than 0.4%, very fast cooling results in martensite. Martensite has a needle-like appearance, is extremely hard, and may lead to dangerous phenomena such as brittle fracture. The transition to the unaffected parent metal in the weld then follows. A next pass, deposited on the first one, causes important effects. We recognize the dendrites in the new layer, the fusion line between this new layer and the first one, finer grains in the center of the first layer, the fusion line between the first layer and the parent metal, the heat-affected zone of the former pass partially annealed by the heat of the next pass, followed by the former Wiedmann-Stetten region, which is transformed by the heat of the new layer, reducing the grain size. Next, a zone affected twice, also by the heat of the new layer, in which we meet degenerated pearlite, a region in which the degenerated pearlite remains unaffected. Then, a region in which the former martensite has disappeared due to the annealing effect of the new layer. A reduction of the carbon content and slower cooling prevents the formation of martensite and so embrittlement. Slow cooling is obtained, for instance, by preheating. Finally, we reach the parent metal again. A Vickers hardness test shows considerable differences in hardness in the heat-affected zones of a single-pass weld and a multi-pass weld. In a weld pool, in particular between the liquid metal and the slag, various chemical reactions take place. Most important are the reactions of iron, silicon, manganese, and carbon with oxygen. Carbon reacts with oxygen, forming gaseous carbon monoxide. During welding, gases such as hydrogen and nitrogen are easily dissolved in the liquid metal. During cooling, the solubility of the gas decreases and the gas tries to escape. However, due to rapid cooling, some gas may be trapped in the weld material, either as porosity or in a supersaturated solution. Harmful gases can be excluded by a shielding gas or slag and gas produced by an electrode coating. Because steel is an excellent heat conductor, welding requires a constant and high and concentrated accumulation of energy. In arc welding, transportation of electric charge between the positive anode and the negative cathode takes place by means of an electric current through the arc. This current heats the arc, and the hot arc heats both the electrode and the workpiece. The visible light is generated by ionized gas. Arc welding can be divided into manual metal arc welding, submerged arc welding, gas-shielded welding, and stud welding. In manual metal arc welding, the arc is ignited by a brief contact between the electrode and the steel. A consumable coated electrode is used, the core of which normally has a similar composition as the metal to be welded. The coating produces slag, forming a liquid protective layer around the drops and on the pool. In addition, a gas evolves which helps to protect the pool against hydrogen and nitrogen in the surrounding air. Submerged arc welding is a more efficient form of arc welding. The arc is covered by a flux layer which also protects the weld pool. A continuously fed electrode in the form of a wire or a strip is used, and a high current can be applied, leading to a high melting rate. Instead of flux protection, gas protection can be used. Three systems are distinguished: MIG welding, MAG welding, and TIG welding. MIG welding is short for metal inert gas welding. As a consumable electrode, a continuously fed steel wire is used, and argon is the shielding gas. MIG welding can also be carried out semi or fully automatically. Closely related to MIG welding is MAG welding, short for metal active gas welding. Here, arc and weld pool are shielded by inert gas, combined with a small portion of oxygen, or carbon dioxide, or a mixture of the two to stabilize the arc. This also produces a smoother weld surface, which has a beneficial effect on fatigue strength. A special application is MAG welding with carbon dioxide only. To reduce oxidizing action, the massive wire contains elements that preferentially bond with oxygen. A disadvantage is the irregular droplet transfer, which results in a rather rough weld surface. Instead of a massive wire, a flux cord wire can be used. The flux contains deoxidizing and alloying elements. TIG welding, short for tungsten inert gas welding, is possible with or without additional welding material. The non-consumable electrode is made of tungsten. The inert gas, usually pure argon, has two functions. It protects the weld as well as the electrode. Without this gas protection, at high temperatures and exposed to the air, the electrode would rapidly oxidize. Preferably, the workpiece is connected to the anode, being at a higher temperature than the cathode. To avoid damage to the electrode caused by contact with the workpiece, ignition of the arc takes place via a supplementary high-frequency circuit. At the same time, contamination of the weld metal with tungsten is prevented. The process is suitable for thin plates for precision welding of small parts and for root passes in thicker plates. Plasma welding is a variation of TIG welding and here applied for connecting the parts of a chimney cladding. A diaphragm between the electrode and the workpiece focuses the arc and so the energy, which leads to burning through the parts to be welded, termed keyhole welding. Behind the keyhole, the parts join. A new development is a TV camera, which can look into the weld to verify the right position of the arc and the filler material. Stud welding is also a form of arc welding. In composite structures, these headed studs form the connection between the steel structure and the concrete. Using a handheld unit, the arc is ignited via contact between stud and flange. Then, the arc heats the stud face and the flange, forming a weld pool. The ceramic ring acts as a form, as protection of the weld pool, and keeps the heating and cooling time under control. Although the process is standardized to a large extent, close control and good workmanship are essential. The main causes of weld defects are moisture, dirt, or rust on the metal contact surface. A special form of stud welding is through-deck stud welding. The stud is welded through a thin steel plate used as formwork in a composite structure, later to be covered with concrete. For quality control, stud welds can be tested by bending. Because cold cracking may occur some time after welding, this bending test should be executed at least 1 day after welding. Though stud welds can be tested by bending, welds are usually tested with non-destructive methods. Visual inspection, to establish, for example, this incomplete penetration, or undercut, or incorrect travel speed, which may lead to cracks. Cracks can be visualized by magnetic particle inspection. A ferromagnetic powder is applied in combination with a magnetic field. A crack disturbs the magnetic field and shows up as a sharp line. Another support to visual inspection is dye penetrant. After cleaning the weld, the penetrant is applied. A long crack. Excessive penetration. And lack of penetration. In ultrasonic testing, sound waves are emitted. The waves reflected by a defect are then received, usually by the same probe. The echoes give information on the location of the defect. The reflection caused by the defect is shown on a screen. A development is ultrasonic testing combined with imaging, in which a separate transmitter and receiver are used. The time of flight method. The crack tips are touched by waves and behave, according to Haugen's principle, as new sources. In the time of flight method, 4 directions are important. These 4 directions are translated in 4 indicated signals. The wave patterns on the screen are translated into shades of black and white. The crack is indicated by wave-like deviations in the gray field between the surface and the bottom of the plate. Ultrasonic testing can be carried out in many situations. The system can be applied in underwater testing of welds. With a set of submerged probes, a rail can be tested. passing through the test rig at production speed. By a peristaltic movement, a crawler containing ultrasonic test equipment can pass through a circular hollow section. Of all weld defects, cracks are the most threatening. A distinction can be made between cold cracking, hot cracking, and lamellar tearing. Cold cracking or delayed cracking is caused by hydrogen in combination with a brittle microstructure as martensite or coarse Widmanstätten, high stresses due to shrinkage, and a temperature lower than 200 degrees Celsius. If one of these factors is absent, no cold cracking can occur. To avoid cold cracking nowadays, special low hydrogen electrodes are produced and constant care is taken to keep moisture out. Hot cracking may occur during solidification due to the presence of low melting phases, mainly at grain boundaries. All weld defects can be avoided by the correct choice of the welding conditions, appropriate material specifications, and by following the correct welding procedure. Lamellar tearing is caused by inclusions present in the steel and elongated during rolling. These flattened inclusions have an adverse effect on through-thickness properties. Imposed stresses due to welding tend to open and interconnect the elongated inclusions. To avoid these cracks, the steel sulfur content must be reduced to below 4 parts in 100,000. Beware, due to loss of ductility at a low temperature and poor structural design causing local stress concentrations, perhaps in combination with an impact, a sudden brittle fracture may occur. Weld defects can be removed manually by grinding, followed by supplementary welding. A special method to repair these defects is hot isostatic pressing. Placed in a vessel at appropriate temperature and pressure under argon, the cracks close or the porosity is eliminated. A clear example of the basic idea behind welding: bonding of atomic structures. However, the dimension of the vessel limits the dimension of the elements to be hipped. Next to arc welding, a special but important welding process is induction welding, here applied in the fabrication of a thin-walled circular hollow section. In the fusion line, a high-frequency current induces resistance heating, while rollers press the sides together until the solidified weld takes over. Due to a small heat input and a small weld pool, shrinkage and stresses are low. Induction welding is a continuous process with a high production capacity. Automation and the use of robots are important trends in today's welding technology. The seam pilot system is a control development in automatic welding. By means of a laser beam, the seam is inspected to conform with instructions and the geometry determined. In the period between scanning and welding, a computer calculates the welding parameters and orientation of the electrode and transmits the correct instructions to the welding equipment. The seam pilot system is, for instance, applied in the manufacturing process of circular hollow sections. First, a steel plate is pre-formed. Then, the full forming of the hollow section follows. After forming, the welding process starts. Firstly, tack welding. And then, submerged arc welding. Inside the hollow section, the torch is guided by a small wheel which easily follows the V-formed seam. However, tack welding spoils the geometry of the root of the outside seam. So, for correct welding, more exact information is necessary. An ideal opportunity to use the seam pilot system. After welding, every hollow section is again shaped to reach its final dimension. The use of robots is also an important trend. It improves weld quality, obtains a constant quality, and increases productivity. By using the robot torch as a sensor, orientation of the torch is possible if the object to be welded is situated within a well-defined space. The torch moves in 3 distinct dimensions. First, vertically, towards the plate and back. Next, horizontally, towards the stiffener and back. Finally, pass the end of the stiffener to find the center of the stiffener and cross-section. All movements are carefully measured, and together with the information on the dimensions of the object and the welding parameters, the computer then has sufficient information to calculate the correct position of the weld and the torch. Welding can now start. Welding, an important process, on and offshore, for simple and complex, but always safe, steel structures.